So we have just seen a talk dealing with the replacement of VME by an alternative technology. Now, what happens with labs which have a significant investment in VME and don't want to move away or need to keep it working at least for part of their installations? Greg Daniluk from CERN is going to give a talk about that. Greg is an electronics designer. Well, I know Greg. So he's an electronics designer at CERN, specializing in FPGA design, gateway design for timing systems and networking. And he's also the leader of a very interesting project called the Distributed I/O Tier, which I invite you to visit in a poster and get hold of Greg and talk about it.
Okay, thank you. So, yes, I will be talking about this, well, quite a long subject. There are two main important things to remember, I think. So, the open source VME bridge and solving vendor locking. So, very quick outline of my presentation today. I will tell you first just a one-slide introduction to VME, for those of you who might not know the standard. Then I will tell you how one event in 2015 changed the VME world for its users. I will give you some more details about the bridge itself, and we will end up with some conclusions. Okay. So VME is this modular electronic standard developed in 1980s. It comes in the form of a 19-inch chassis that you mount in the rack, and then you can populate it with many cards. Those cards slide into the crate, and they communicate together over the backplane that you can see here on the slide. So in the backplane, we have something called a VME bus. This is a bus of the master-slave architecture, so we can have, in principle, several masters. We, in our installations, always use it with a single master board, and then this one communicates over the backplane with many slave cards. So master is what we call a single board computer, okay? And then the slave cards, depending on your application, those can be either off-the-shelf modules, or you can also design your own boards. And just to give you a few examples, these can be ADCs, DACs, time-to-digital converters, basically whatever you need for a particular application. Now, the bus in the backplane is a shared and parallel bus. It can give you, for the base standard, without the extensions that came later, you can reach up to around 80 megabytes per second transfers. But since the bus is shared among all the cards, of course, if you have system fully populated, the actual performance is much worse. So then, even if it is quite an old standard, it is still widely used in places like research institutes, like CERN, in military applications as well. And just to give you some numbers, currently at CERN we have around 900 VME crates deployed only for the accelerator application. So this does not count all the VME crates deployed for the experiments. And we still plan to deploy 200 new crates in the context of Long Shutdown 2, which will happen in 2019-2020. Yeah, so I mentioned that the master for the VME crate is a single board computer. What is it? It's basically like a regular computer, like your laptops. So it has a processor, it has some DDR memory, it has interfaces like USB, like Ethernet. Now the difference is that it has this connector on the top, the VME connector, to let it communicate with other VME cards. And the issue is that the processors that we have, they don't speak VME bus. They can do PCI Express, but not VME. So on the single board computer, we need one more chip called the VME bridge. And this one basically translates the PCI or PCI Express bus to VME bus. So at this point, you might already start wondering, why is VME still alive? It is quite an old standard with, let's say, very limited performance. We have many more modern standards for modular electronics. We have micro-TCA, we have PXI Express, several others. So there are several reasons for that. First, there is already quite a huge investment in the technology in places where the lifetime of electronics is quite long. We at CERN, when we design new boards, new electronic modules, they will live in the accelerators for the next 10, 15, maybe even more years. Then we very often design custom electronics for VME for very critical applications. So we put a lot of effort to test them well, to validate them for those systems. And once we are done, we are really reluctant to redesign this to another form factor, especially if the performance of VME is sufficient for those applications. Okay, so what I just described to you is quite a stable environment of well-established standard over the years. And this was true till 2015. So then there is a story of this TSI-148 chip. Okay? So this is a PCI to VME bridge that was the de facto standard in the VME world. And it was used in many single-board computers, including the one that we used at CERN, so MEN 820. I said it was the de facto standard because mid-2015, IDT decided to discontinue the production of the chip. So this was a problem for us because we were not able to ask MEN to produce more single-board computers. And in the same time, of course, we were getting more and more requests from our users to provide them with VME-based systems. So also, in the lack of this de facto standard, we were afraid to go to the vendor locking situation where we would be tied with some proprietary solution, bridging solution, tied to a particular single-board computer. So what we did was a call for tender, and we asked potential bidders to provide us with single-board computers for the next 5 years of CERN's operation, and we gave them 3 options. Okay? So the first one was you should secure enough stock of TSI-148 to provide us with a specified number of boards. Or you could use the Tundra Universe 2 chip, which was a predecessor of TSI-148, but still in production. Or you could make a single-board computer using the FPGA-based implementation of the VME bridge, and then we ask you to open source the implementation. So we gave no preference to any of those options. So from those companies who qualified for the call for tender, we selected one offer that was the best price. And this one turned out to be option number 3. So the company that was providing us with the previous generation of boards, they now had a new generation called MEN 825. And for this one, they made their own implementation of the VME bridge in the FPGA. So after they won the contract, we started working with them to open source the implementation and to validate it for our systems. Okay, so this is the actual board. So under this big heatsink, there is Intel Xeon processor, some DDR memories, and then here in the bluish square, there is the Intel Altera Cyclone 4 FPGA, where this VME bridge lives. Then the board also has some PMC and XMC connectors, so you can expand it if you want to have, for example, another Ethernet card or VGA output. Okay, so some words about the VME bridge. On the current hardware platform, so MEN 825, it takes around 30% of the Cyclone 4 FPGA resources, which means even on this board, we still have plenty of space to still add new features or to modify the design if we need it. Some bullet points for those of you who are more familiar with the VME standard. So it supports VME single cycles, it can do block transfers, and these ones are executed using the DMA engine, also implemented in the FPGA. Then it supports geographical addressing, and it can access CR/CSR configuration space for the slave cards. What is currently not implemented are the extensions that came later to the VME standard for the fast data transfers. So no 2E VME and no 2E SST for now. Okay. So quick look on the top design of the FPGA-based bridge. It doesn't look that complex. The complexity is inside those modules. So there are, in principle, several VHDL modules communicating together over the Wishbone bus, which is this open source bus for FPGA projects. And there are 2 main modules. There is the PCI Express implementation. So this one This one configures actually the hard IP core for PCI Express that is in Cyclone 4 FPGA. And then there is the VME bus implementation, and this one also includes the DMA engine I mentioned for the block transfers. Then we have several smaller modules, so the flash interface to let us remotely update the FPGA firmware. We have the SRAM controller to access the external RAM chip for the DMA accesses, and there is also a small module just to hold the revision of the FPGA firmware. Now, all the sources of this breach, of all the VHDL sources, are published under GPL03 or later license, and this also applies to the set of VHDL test benches. So we asked MEN to also provide us with test benches so that later, if we want to expand the design, if we want to add new functionality, we have some regression tests, we can do the simulation. So what comes with that is also the software package, and this one is licensed under GPL2 or later license, and so this is to comply with Linux kernel licensing scheme. And in the software package, you will find a set of Linux kernel drivers, and you will also find this tool to be able to upgrade the FPGA bitstream from the host system running on this single board computer. Okay, now so to conclude, some few messages to take home. VME is still alive, and it will be still for the next some years, and we plan to use this VME bridge in the FPGA to support our CERN users for the next years of CERN operation. Since it is an open source solution, it solves the VME bridging problem not only for us, for our installations, but also for everyone who still uses VME, and it solves the VME problem, the bridging problem, forever, or at least till the end of the VME bus life. Okay. Since it's open source, also everyone can produce a compatible single board computer, so you don't have to even buy this MAN825. You can anytime take the same bridge and ask any other manufacturer to produce different single board computer that would be still compatible, would have the same API, would use the same kernel drivers. And of course, anyone is free to add new features. I mentioned that currently there are no extensions for fast transfers, but we can add it at any time when needed. So yes, now we believe we would like to invite you to join the community, and yes, let's build the community around this project. So you can go to this project page where you will find more information, and you will find all the sources for the VHDL and also for the drivers. Thank you.
Time for questions.
Hi, Greg. First question, I have several, so maybe we will even talk later.
Okay.
But maybe two. So one thing, why there is no white rabbit on this controller? And the second, how is it related to existing VME implementation which is used for SFEC boards?
For which board, sorry?
SFEC.
Well, SFEC is a VME slave.
It may be also master. It might be.
Well, it has FPGA, so I mean, yeah, in principle. Okay, so this one is a single board computer, so you have not only FPGA, but you have processor, and you can run Linux, Windows, VxWorks, whatever you want. SFEC is an FPGA-based FMC carrier, so it is meant to be used as the VME slave. So yeah. Okay, this one actually, this VME bridge, it could also act as a VME slave. Yes, but okay, I mean, if you want to have a single board computer for VME, this is the one to use.
Okay, because in VME there is only distinguish thing that the first slot is for arbiter and the master might be any of the board.
Yeah, so this one is like master/arbiter in one device. Yeah.
And why there is no white rabbit in it?
Why there is no white rabbit? Because you have SFEC that can do white rabbit.
Yeah, but then you have two boards.
Yes, but the smallest VME crate is anyway 2 slots. No, yeah, I think I don't have a good answer to why there is no white rabbit on this one, but yeah. Yeah, I mean, you are always free to design. We don't have yet the White Rabbit mezzanine in the PMC or XMC form factor, so this would be an option. You will have? Yes. Oh, okay, perfect.
Let's have one last question from
Okay.
Eric. I think Eric wanted to ask a question.
Sorry.
So did you preserve the software interface? Is it still compatible with the TSI 141? So for example, instead of Linux, we were using RTEMS as an example. Would we need to make any software modifications to use your chip?
Mm-hmm. So actually what we did, because for the MAN820, so for the TSI 148 at CERN, we had our CERN driver for it, and what one of our colleagues did was writing like a wrapper kernel module that preserves the original interface and then acts on or translates it to the MEN drivers for this new bridge. Yeah.
Okay, let's thank Greg again.